Okay, so welcome to the last session for the 2019 String Math Conference. So I just have one announcement to make. Apparently, after the break, they're going to come and take away all the posters. So if you really love your poster, please go get it. Otherwise, it's gone. So anyways, we're happy to have Sara Pasquetti. And she'll talk about from 3D dualities to 2D free field correlators and back, and an E-string surprise.
Okay, so thank you very much. First of all, I would like to also thank the organizer for putting together this very nice meeting and inviting me to speak. So today I will present some work that I've been doing with various postdocs that were in Milan at certain points. My student Matteo Sacchi, who's in the audience, and some work in progress that should appear soon with Shlomo Razamat and Gabriel Zafrir. So I thought that I should just start setting up some terminology, especially if there are mathematicians in the audience. So my talk is going to be about dualities and correspondences. So for me, in this talk, dualities will be really infrared dualities, like cyber duality, where we think about two theories that are different in the UV, but then in the infrared they look the same. Of course, this is a very important concept in theoretical physics, and because it allows often to probe systems that are strongly coupled and to find a new set of degrees of freedom that can be weakly coupled to describe this system. So if we want to investigate infrared dualities, we need non-perturbative okay, burn one pointer already. Oops. So we need non-perturbative techniques. We can match anomalies, try to map operators, protected operators, and since more recently we have also the possibility to calculate quantities via localization and map also these exact quantities between dual theories. So this is a very important way of testing dualities and discovering new ones. I will be also talking about correspondences. So although there is also a more physical way to think of correspondences as coming from some bigger theory compactified on product of spaces, for this talk, for me, correspondences, like AGT, will be really about the possibility of establishing a dictionary to map exact quantities that, for example, you can calculate with localization in some supersymmetric gauge theory to objects that instead you can define in some other system that could be 2D conformal field theory, a topological quantum field theory, or some integrable system. So in both cases, localization is somehow playing an important role. As you know, the idea of localization entered the world of physics since from the 80s with Witten, and there has been many applications, and more recently, I would say since 2007, thanks to the work of Pestun, people started looking systematically at supersymmetric gauge theories on compact manifolds. Now, when you want to do so, basically you have to do it's a two-step process, really. First of all, you need to formulate your theory on some compact space, and this at the beginning was done in a sort of ad hoc fashion, and then a more systematic approach has been developed, and this very nice approach has been initiated by Festucci and Seiberg. Once you are done with the definition of your theory on some compact space, then you have to implement the localization procedure, and in the end your problem really boils down to calculate some one-loop determinants. And this, in the end, can be rephrased as re-expressing these determinants in terms of special functions. So there is a very nice review that you can consult that has been put together by Maxime and Pestun, where somehow it collects what has been going on in the field from 2007 to 2017. It's really lots of contribution. In particular, I want to steal from the introduction that Vasily and Maxime wrote this nice slide where basically they observe that as the results were coming out, localization done on different spaces would produce, results that look very different. But as the time passed and the dust started to settle down, it was, realized that partition functions on different spaces are very often written in terms of families of special functions. For example, here I'm considering the case of spheres in even-dimensional spheres or odd-dimensional spheres. So it turns out that when you do localization, in the end, the partition function on these spaces, different dimensions. So notice that here we are talking about theories that may have a different amount of supersymmetry in different spaces. Nevertheless, their localized partition function, they take somehow form where you just have typically two families of special functions, one known as multi-gamma functions and one known as multi-sign functions. So I think is nice. What is also nice for us physicists is that sometimes mathematicians have studied the integral involving this special function, and they work out amazing, identities for these integrals, which for us really it's great because they already done the work that for us amounts to prove dualities. So a duality in field theory, then when you perform localization, then translates in a statement that two partition functions that become matrix integral, they have to be equal. And this work, in some cases, was done for us by mathematicians such as Spiridonov and Rines, who studied this type of integrals. Okay, so I was trying to make the point that there are dualities and there are correspondences, and there are two very different objects. And now I will try to confuse you a little bit to show you that in some cases you can go from a duality to a correspondence, and you can also go back and learn something. So at the beginning, I will ask you basically to follow this naive game that I want to play, and maybe I will try to tell you why this makes sense and why it can be useful. So the context where we actually learn that you can go from a duality to a correspondence is a specific situation, which is a quite nasty situation. We were trying to study what happens when you reduce a three-dimensional theory, a three-dimensional inequality theory on a circle. So then basically you go down to a two-dimensional theory, some 2,2 theory. And these people here, they wrote some paper that I think were trying to scare you off from really studying this subject, because it's very hard what happens when you reduce to two dimensions, especially if you have non-compact branches. Your life can be quite complicated. So I refer you to this paper to see the subtleties of what happens in two-dimensional theories, and instead I ask you to play this game with me, which is instead focusing on partition functions. So I don't make statement in field theory at this stage. I really focus on localized partition function of three-dimensional inequality theory on spaces like disk times circle or spheres times circle, where I turn on all possible mass deformations in my theory. So the theory don't have modular space, they have isolated vacua. So on these two spaces, the one-loop determinant that appears in localized partition functions are written in terms of this type of functions. These are Q factorial functions. So these are the building block that appears after the localization procedure. Now, when you want to reduce on a circle, so this parameter Q is basically e to the radius of the circle, you have to decide how the parameters, the real mass parameters that appear in your 3D theory scale with the radius. So you have various possibilities. There are typically two limits that you can implement that make sense, of course, also in field theory. You can decide to keep the matter field lights and to leave the Coulomb branches. This type of limit is the limit that would typically reduce your gauge theory in 3 dimension to a gauge theory in 2 dimension. And the limit is implemented basically by this type of limit on ratios of Q factorial that leads ratios of gamma functions. So the gamma functions are the building block that appears instead in partition function onto spheres and disk. There is also another limit that you can take, where instead you make your massive field heavy, matter field heavy. And this is the limit where instead you would expect to land, instead of on a gauge theory, in two dimension on some Landau-Ginzburg model of twisted multiplets. However, I ask you not to think that way. I ask you just to look at what happens when you take this type of limits on the partition functions. Now the parameters are scaled differently, and the ratios of Q factorials that you have in the partition function, they become an expression of this type, okay? Something of this form. So if I wanted to think this as a Landau-Ginzburg model, maybe I would exponentiate this and try to recognize this as some superpotential term. But instead, I'm just suggesting that if you find with an integral of pieces like this, if you have been working sometime in conformal field theory, you recognize this as ingredients of some free field correlators, like those that appears in minimal model, for example. Okay, so how can I convince you that this makes sense? So first of all, what this type of possibilities of taking the limits means that if you want to study the reduction of dualities, you have various possibilities. If you start from a duality like are only dualities in 3 dimensions, then in this case, if you want, you can implement a limit, the same limit on both sides you can apply. You can scale the parameters in the same way on both sides of the duality, and you typically land on something that looks like the same gauge theory but in 2 dimensions. You can also take this strange limit where you scale the parameter differently, and you would land on a relation between Landau-Ginzburg model, but I ask you not to do so, but to think that you land on a duality identity between free field correlator. Or if you have another type of duality, like mirror duality, where the Coulomb branch and the Higgs branch are swapped, if you take a limit of, say, Higgs type on one side, you are forced to take a limit of the different type on the other side of the duality. And this inevitably lands you on something which is a relation between a gauge theory on one side, like a GLSM on one side, and on the other side you would expect to get something like a Landau-Ginzburg model. So you would think you would get Hori-Vafa duality, as indeed is known that starting from 3D mirror symmetry, you can get a Hori-Vafa dual pair in 2 dimensions. However, if you think the way I'm suggesting, I want to reinterpret the Landau-Ginzburg side instead as a correlators of free fields. So I expect from this type of duality to land on correspondence that connects GLSM partition function to a free field correlators, more in the spirit of IGT. So that's more or less the idea that we want to follow. So let me start first discussing how, if we start from spectral dualities, we can end up on gauge free field correlators. So spectral dualities are a type of duality which is similar in spirit in mirror dualities, because in this type of dualities you swap somehow the Higgs and Coulomb branches. So when you take the limit to 2D, then you face this phenomenon that you cannot take really the same limit on both sides. You are forced to take the limit differently. So how do I define spectral dual pairs? So I want to construct, first of all, some type of 3-dimensional theory, 3-dimensional unequal to theory, as a defect theory, as a codimension 2 defect theory in a 5D theory. So the 5D theory that I have in mind, for example, it's a linear quiver with nodes UN. So this type of quiver theory can be engineered on a PQ web of brane. And one way to realize a codimension 2 defect theory is to think that you can remove some of the NS5 branes from the PQ web and stretch D3 brane between. Now, if you look at the theory that lives on the stretched D3 brane, that's the theory that I want to focus on, like my codimension 2 defect theories. So, for example, here I'm focusing on a particular defect theory that we name FTSUN. So it's a quiver theory with nodes U1, U2, U3, and so on and so forth. So this is very similar to the TSUN theory, which was introduced by Gaiotto and Witten as the boundary condition for super-Young Mills. But you have an extra set of singlets fields, this Xij, that couple to the mesons. So this is an n equal 2 theory that lives on this setup, which involve NS and the 5' branes. So this is an n equal 2 theory. So like TSUN, which is n equal 4, is self-dual under mirror symmetry, this theory is also, this 3D theory, FTSUN, is also self-dual, and it inherits this property from the fact that this PQ-web is invariant if I exchange NS5 and the 5' brane. So this theory is also self-dual. And we give a name to this type of duality that relates this type of 3D theory. We call it spectral duality to distinguish from mirror symmetry, although it shares some feature with it. In general, mirror pairs and spectral pairs are different. So what is good about this setup, that this realization of spectral dual theories, is that I can use two ways to study these theories. So I can either use purely three-dimensional field theory methods, so I can study the duality by mapping operators or calculating partition functions in 3 dimensions, or I can use geometric engineering, so I can study the 5-dimensional theory, indeed on this brain setup that can be uplifted to some geometric engineering of compactification on some toric Calabi-Yau, which has the same toric diagram as what you would read for the PQ-web. And then I can implement this operation of removing basically the NS5 from the PQ-web and stretching the tree at the level of the Calabi-Yau by saying that in the toric Calabi-Yau, some of the Kähler parameters are quantized to special values. So this is just what is known to most of people as the phenomenon of geometric transition. So I can calculate the partition function on this Calabi-Yau threefold, where I tune some of the Kähler parameter to special values. So in this case, I'm tuning the Kähler parameter that are labeled by black dot to make them proportional to basically 1 to 1. So here I'm talking about a refined topological vertex, but that's like the equivalent of like having just one stretched D3 branes, whereas the gray dots mean empty intersection. So if I implement this specialization of the Kähler parameters, then I can really show that the partition function on this Higgs, if you want, Calabi-Yau, matches the partition functions of the 3D theory. Good. So the Calabi-Yau is obviously invariant if I exchange the Kähler parameters and the fiber parameters. So this is the fiber-based duality that holds at the level of topological same partition functions, and this property holds before and after I tune the parameter to go to the specialized point in the moduli space. And you see that since the partition function of the topological string at specialized value is the same as the partition function of the 3D theory, I can infer the duality that relates to 3D theory from a property that belongs to the 5D theory. So in this sense, I mean that 3D duality, like spectral dualities, descends from fiber-based duality. Hence the name, which we picked this name, spectral duality. Okay, so this is just probably the simplest example of a spectral dual pair that one can construct starting from 5 dimension. So I want to continue discussing this example for a moment. So in particular, I want to ask what happens at this point if I have these pairs of 3D spectral dual theories, this FTSUN theory, when I compactify down to 2 dimensions. So as I mentioned before, I can take the so-called Higgs limit, which is this natural limit that takes your 3D gauge theory to similar gauge theory in 2 dimensions. And this is what I get on one side of the duality. And I can take the same limit, and I can take then the limit also on the dual side of the spectral duality. But this limit, since I swap the parameters which were the fiber parameter with those that were the base parameter, which in the gauge theory were the mass parameters and the Fi parameters, then the limit takes a completely different form, and I land on something that I recognize as a free field correlator. So I get out of a limit of a 3D duality, I land on a relation between a correspondence between a GLSM, which has this, which is this quiver theory in 2 dimensions, and a free field correlators with 2 primaries which are fully generic and n primaries in between which are instead degenerate. And I have also a number of screening integrals insertions. So really here, I'm recovering what I would expect from the AGT map from a codimension 2 surface operator and some correlator involving degenerate operators in Liouville CFT, which I'm here representing as a free field correlator. So I should say, okay, here, this construction can obviously be generalized. You can construct many more examples of spectral dual pairs of theory if you start from different brain setup and you do this Hicksing procedure, then you can obtain dualities between gauge theories that you can again study with field theoretical methods, or you can infer from the properties of the 5D partition functions. In these cases, again, when you reduce down to 2D, you find correspondences from, on one side, some GLSM, and on the other side, you land on some free field correlators. So probably this story can look a little bit weird, but in the end, if you are familiar with this work that was by Aganasic and Hautzi, Kochkatz, and Shakirov from a few years ago. So these people already established a correspondence between quiver theories, 3D equal to quiver theories, and free field correlators, where, however, you were supposed to turn on some Q deformation. So their stories combined with the spectral duality, in a sense, is explaining you why, starting from spectral duality, which is a 3D infrared duality, you land on a duality, a correspondence connecting GLSM and free field correlator. So this was basically one of the possibilities that you can encounter when you reduce spectral duality, so in this particular type of 3D duality from 3 dimensions to 2 dimensions. But there is also another possibility, which is what happens if you instead focus on more standard dualities like Aroni dualities or 3D cyber-like dualities in general. What happens when you reduce them to 2D and you want to play this game of reducing in such a way that you land on something that reminds you of a free field correlator? So the dualities that I want to focus on are these 3 dualities. Well, they are only dualities that should be very familiar. You have some variation on the theme where you can also take linear monopole operator and turn them on in the superpotential. So these 3 dualities, they can all be obtained, in fact, as a limit to 3 dimension of a 4D interligator Puleo duality relating USP to N for the USP to N theory with 2N flavors, plus various real mass deformations. Okay, so the observation that we have is that if you take this duality here, actually the duality with 2 monopole operators, is very easy to turn on some real mass deformation and recover the duality with a single monopole operator turned on in the superpotential, and also the Aroni duality where no monopole operator are turned on. So in a sense, this I want to think as this my master duality. So if I take this master duality and I calculate and I consider its superconformal index, so the partition function on S2 times S1, if you implement this limit, which is not the canonical limit that you would implement to go to 2 dimension, you may land on this complex integral, this identity between complex integrals. Now, it turns out that this type of identity between complex integral appears in other contexts. So it appears, in particular, in the work by Fatev and Litvinov, in the business of conformal field theories. Okay, so here you have two-dimensional complex integrals. And you see that the data that were in the field theory, in 3D field theory, are still here. Somehow you have the number, the color number, the flavor numbers, and you have some parameters that were the real mass parameters in your 3D theory. So we ask, okay, let's see how these CFT people were using these dualities. And in fact, the use of this duality was kind of interesting, and they appear in particular in the way you derive the 3-point functions in Liouville theory. So let me tell you a story that probably you already know very well. So it was not very long ago that if you take a correlator of primary operators in Liouville CFT, if you perform an integral on the Liouville zero modes, then you notice that this correlator has poles when the sum of the momenta of your operator satisfy the so-called screening condition. So when this condition is satisfied, this correlator, okay. So this correlator has a pole, and you can evaluate the residue. You can notice that the residues at this pole, it's equal to an integral in that you can. Okay. So this correlator, when this condition is satisfied, takes the form of a correlation function in free theory with insertion of n screening charges. Okay, so now you are supposed to calculate correlators in a theory of free bosons. So now it's easy. You can take your free boson and expand it in normal modes, normal order it, and then this integral, this correlator, becomes a complex integral. This is what comes out, the operation of normal ordering your operators. Okay, so the goal is to evaluate this type of integrals. Not only you would like to be able to evaluate the integral and then to do analytic continuation in n, so that you can lift the screening condition and reconstruct fully your correlator. So that's the idea that you need to have in mind. So how do you go about it? So this problem was attacked already with several methods. So the first problem indeed how to evaluate this type of complex integrals. In a sort of recent work, dates 2007, work by Fatev and Litvinov, the way this integral was evaluated was to using iteratively this identity between complex integral that I showed you before. So if you use this identity, you can reduce your n-dimensional integral to an integral of dimension n-1. So reduce the number of integration, and if you do it, this procedure n time, you can actually arrive at an evaluation formula for this complex integral, which involves product of this little gamma function. Now, here you are not done. If you want to find the 3-point function, you want to do analytic continuation in n, remember, lifting the screening condition. The way to go, of course you need to be quite smart, as Fatev was, is to think that you can trade this dependence in n that appears in the product for a dependence in n inside the argument of some other function that satisfies some periodicity property. So it turns out that there is a function, let's call it capital Upsilon, that satisfies some periodicity property, and you can repackage the product of n of this little gamma function in terms of product of some of this Upsilon function, where the dependence on n now is hidden in the argument. So alpha is the sum of all the momenta that satisfy the screening condition. Okay, so now the dependence on n is now inside the argument, and you are good, because at this point you can do analytic continuation. Of course, you need to check that the way you did this trick is really the solution of your problem. You want to check all the set of poles that this theory, that this function has, but it turns out that that's really satisfying all the properties that you want to have for your 3-point function. So this is how, you can derive this Liouville 3-point function. And I'll remind you that the first step was to iteratively use this basic integral between complex, identity between complex integrals. But these identities for complex integral is really the limit of a 3D duality. So can I go back? Can I try to mock what is done in the CFT context and try to follow the same logic and see if also the evaluation formula for the three-point function has an interpretation as in field theory? So I'm doing something quite weird. I'm thinking that I have a formula that connects complex integral. It's just an identity, and I want to uplift this not to an identity only, but to a duality between field theories. So here is the guess that I want to put forward. There was a recently proposed duality by Benvenuti that relates is a duality in 3 dimensions that connects a UN theory to it one adjoint, one flavor, and there are some singlets operator that are flipping the Casimir of the adjoint. This theory is conjectured to be dual to a Vest-Zumino model of 3n fields. So you have 3n operators that enter in a cubic superpotential, and so you can establish a map of the operators between these two theories. For example, you can map the monopole operator dressed with the adjoint to the singlets. You can also map the mesons to add the other singlets. So the claim is that if you take this duality and you study its partition function on S2 times S1 and you reduce it to 2D, then you really get this evaluation formula for the Liouville correlator. But not only, I can really repeat the logic that is behind the way that the free field correlator was evaluated to come up with a new proof of the of this identity. So the idea is that I can start from an auxiliary quiver theory in 3 dimensions and start iteratively applying the basic dualities, like the duality that with one monopole that confines the first node and leads me to the original theory, and then alternatively I can apply the Aroni duality to this node, which lower the rank of the theory to n-1. So at every step I produce some singlets operator, and if I iterate this n times, I get finally the Vest-Zumino dual model. So okay, so once you have, you understand the logic, okay, so basically the logic here is that there are some identities that are worked out in the context of the CFT, and I want to reinterpret them as dualities in 3 dimensions, and this makes sense. Actually, it gives you some mileage. You can learn some new tricks. So in particular, I would like to show you an next example, so which is still studied by Fatev and Litvinov. You can consider, for example, what happens if you take a correlation function which involves 3 primary operators and a bunch of degenerate operators. If you try to study this with a free field approach, you would first of all write this as a screening integral with n. So a rank n screening integral. However, as your goal in the end is to be able to do analytic continuation, so you have to massage this integral in some smart fashion, and this is what these people managed to do. So they rewrote the original screening integral in terms of a function that they named the kernel function. It's a very interesting object, which has some remarkable properties. So it depends on 2 sets of k variables for when you have this kernel of dimension k. You also depends on some other variable c. Now this function has some property, and in particular it's invariant if you swap these 2 set of variables. Now, basically, from CFT you learn that you can re-express an n-dimensional screening integral as an integral involving this very nice kernel function. So the idea now is that also this can be given a new life as a three-dimensional field theory statement. So let me take you through this slowly. So first of all, this function K, the kernel, I claim that has an avatar as a three-dimensional equal to theory, which is described by this quiver here. So it's a quiver with nodes U1, U2, UN minus 1. At every node there is some adjoint, and in the superpotential at every node I turn on the fundamental monopole operators. And then there are some flavors also. So the idea is that this theory has a very non-trivial global symmetry. So the global symmetry group in this theory, thank you. Okay, thank you. So this theory has a obvious SUN symmetry that rotates these flavors, but it also has another SUN that is emergent, that is only visible in the infrared, because in the UV you only see its cartan, which rotates these flavors. And then you have two extra U1 symmetries. Now, this theory has a property that if I turn on a mass deformation for one of these U1 symmetries, for this symmetry, it reduces to this familiar TSUN theory, or FTSUN theory, that was introduced by Guyot and Witten. So you can understand that these limits basically integrates out, make heavy all the of this flavor in the SO. And, of course, it reduces to this kernel function that was introduced by Fatev and Litvinov. So this theory has some non-trivial properties. For example, it is self-dual. So it is self-dual and under a duality that swap the two non-abelian symmetry. So in particular, you can convince yourself about this by looking at the operator of these theories. You can easily construct operators that transform in the adjoint of one of the SUN symmetry, for example, by putting in a matrix all these mesonic operators that you can construct with the fields, and you can figure out that they transform in the adjoint and they are swapped under the action of this duality. And you can also just match, for example, the superconformal index of these theories. And it's okay. So the idea is that now that you have this interesting object, this interesting theory, you may want to use it to study new theories. So it could be your new building block to construct theories. So I want to just define a new link which has symmetry SUN squared times U1 squared, and the idea is that I want to be able to use it to construct theories by gauging not only its manifest symmetry, but also the emergent symmetry that I realize that this object has. So, for example, one example of theories that I can construct using this gadget is really, as promised, the 3D avatar of the duality that involved the identity that involved the 3 plus k point correlator. So remember, in that case, so we had an identity that connected on one side and an integral. On the other side, we had an integral involving this kernel function, which I tried to convince you that can be uplifted or reinterpreted as a 3D self-dual theory. And this relation can be reinterpreted as a duality between gauge theories, which is a generalization of the duality by Benvenuti, where on one side you have a UN theory with k plus 1 flavor. Some of these flavors are coupled to the adjoint, one is not. And this theory is conjectured to be dual to this link made out of this quiver theory, which is further gauge with another flavor. So that's a non-trivial duality where you can work out the map of all your operators, and you can test partition functions. So you can keep going, right? So at this point you can think, okay, I can construct more interesting theories using this building block. that's something that we are thinking about in 3D, but there is an exercise that immediately comes to your mind that you want to do, because I told you that the basic dualities that I originally identified with the duality that leads to the complex integral identity that appear in the CFT, I mentioned that this duality can actually be understood as coming from a four-dimensional duality. So you can think that, well, maybe the whole story can be uplifted to 4D. Maybe I can find a four-dimensional ancestor for everything here. In particular, can I find an uplift of the kernel function as a four-dimensional theory? So the answer is yes. There is a four-dimensional quiver theory that I can consider. So it's a quiver theory where every node here is a USP2n. So the first one is a USP2, USP4, and so on and so forth. And then there are some flavors. These dashes here indicate that there are some singlet coupled to these mesonic operators. Again, the statement is that this theory has a non-trivial global symmetry that is appearing in the infrared. So you have a manifest USP2n that rotates the flavors. You have another USP2n that is emerging from, and in the UV is only visible, a product of USP2. And you have two U1s as well. So this theory, when it is reduced to 3 dimension, becomes the 3-dimensional avatar of the kernel. Okay, and in turns, by further deformation, becomes the TSUN theory. But what is interesting is that if you take the superconformal index of this theory, this is also an object that appears in mathematics in apparently an unrelated context. It appears in the work of Rines, works of this year actually, and it is named the interpolation kernel. So this kernel is basically related to interpolation function, this R, which in a sense they are a generalization, sort of a elliptic generalization of Macdonald polynomial. So Rines proves in his paper some very nice properties for this kernel function that, again, for us are a way to learn about the properties of this four-dimensional n=1 field theory. For example, this field theory in 4 dimensions is also self-dual under a duality that swap the two non-abelian symmetries. Again, you can do the exercise of constructing operators, transforming in the anti-symmetric representation of the two USP2n groups and try to map them. Or you can just look at the indices, and this time Rines did for us the non-trivial work of showing that the superconformal indices of these two theories are equal. And you see, again, this is implementing the fact that these functions are symmetric in the exchange of the two sets of fugacity that are in the Cartan of the two USP2n symmetries. So there are various, obvious thing to do at this point. You also want to think at this theory as a building block to construct more general theories. In particular, there are more properties that were discussed by Rines that you can uplift to statement in field theory. For example, this block is in the lowest rank case, in the rank 1 case, is just an SU2 times SU2 bifundamental. And there is also the property that tells you that this block, if you turn on some VEV, actually collapses into a USP2n times USP2n bifundamental, plus some singlets. And there is also another curious property that tells you that if you glue two of this block with some doublet, then this is really, again, going back to itself, times some extra fields. Rines calls this property the braid property of its kernel. In particular, in the rank 1 case, is just like Seiberg duality. Okay, so I was kind of going around asking people, like, do you think we can construct interesting theories with this building block? And I was lucky enough to ask this question to Shlomo Radzamat, and he told me, yes, I think we can construct rank n E-string compactifications. So let me just quickly say something about how this enter the topic. So there is a very, interesting program, which is that of realizing four-dimensional field theory starting from a mother six-dimensional theory compactified on some Riemann surface. This program has proved to be very successful. You can learn a lot about four-dimensional field theory starting from 6D. You can learn about the importance of non-Lagrangian theories. You can learn about pattern of emergent symmetries, dualities. So it's definitely a very, fruitful approach. In particular, if I give you a certain six-dimensional theory, it could be the 2,0, some 1,0 theory, and you also give the details of the compactification, so what type of Riemann surface, what type of punctures you have, then you can make very precise prediction for what your 4D theory should be. So you can predict what the symmetry should be, you can predict what the anomalies should be. So, in a paper by Kim, Ramazamat, Waff, and Zafrir, the 6D theory of choice was the 1,0 rank n E-string theory. So, this is a theory that lives in 6 dimensions as E8 times SU2 symmetry. And they studied a case where this theory is compactified on a torus, turning on some fluxes in the cartan of E8 and breaking the E8 cartan to breaking E8 to some subgroup. And with this setup, you can also predict, that if you do this compactification, a certain four-dimensional equal one theory with these characteristics should exist. So you expect a gauge group, global group that is a subgroup of E8 times SU2, and you have also prediction for what the anomaly polynomial is. So then the point is that can you also directly in 4 dimension construct a theory that fulfills this prediction coming from 6D? So in the case of rank 1, they managed to construct purely in 4 dimensions this type of quantum field theories. The idea was to start from a building block, which is basically the torus with 2 punctures. So they had that's their building block. It's just an SU2 bifundamental with some octet and some operators and some fields. The claim is that by gluing these tube theories, they can realize torus theory with some unit of flux preserving, for example, E7 times U1, which is in the case where you preserve the maximal amount of symmetry from E8. Okay? So then if you turn on more general fluxes, so you break further E8, for example, you can have E6 times SU2 symmetry, you can achieve it in terms of more general gluing of this fundamental torus building block. So they had this nice construction where they realized these torus theories, and they can compare, for example, the anomaly polynomial calculated from the field theory in 4 dimensions to the calculations in 6D. What was missing in their picture is like how to go to higher rank. So they were not able to construct the theory in 4 dimensions that meets the prediction of higher rank E-string. Well, the idea is that if you take this building block, which is the famous avatar of the kernel function that appears in the CFT, or the Rhine's kernel function in 4 dimensions, so this building block theory, which is this USP2N quiver, then you can realize the tube for higher rank E-string. So if you then start gluing these tubes and you make tori theory, you can construct theories with global symmetry, which is given by a certain subgroup of E8 times SU2. So crucially, you're also able to see the extra SU2 that appears in the higher rank case. You can then start calculating anomalies and match all the predictions that you make from 6D. And again, you can also consider other types of gluing that describe cases with smaller symmetries. Okay, so I think I'm done. I think the observation here is that there was a certain amount of mileage that we're able to take by looking at mathematical objects like the kernels that Fatev and Litvinov introduced in the study of complex Selberg integral that appear in the study of free-field correlators, or studying or looking at the kernel that appears in the work of Rhines, and somehow in a sort of non-really canonical way, we could associate or reinterpret this mathematical object as statement in quantum field theory. And from this, we could construct new theories and learn about new dualities. So hopefully, maybe we will be able to give back something to the mathematician using the field theory perspective that allows us to think more uniformly about all these corners, because for us it's very normal to think of going from one theory to the other by compactification or turning on some RG flow. Okay, I think I stop here.
Okay, we have time for a few questions. Well, if not, let's thank Sara again.